Hi, hello, welcome back. Today we are talking about a very important topic in chemistry, and that would be this idea of a mole. All right, I'm going to start right away and take the mystery out of this idea of what a mole is in chemistry. A mole is just a number. So, just like you are familiar with a dozen is just a number, it is 12. Well, a mole is just a number. Moles, or when we talk about moles, or singular mole, it is just a number. It's a huge number, 6.022 or 23 times 10 to the 23rd. So it's just a gigantic number, astronomical, but it's just a number. Okay? It's a fixed number. A mole is always 6.022 times 10 to the 23rd. That's also called Avogadro's number because of the scientist who discovered it. Just like a dozen is always 12. Okay? So, how do we count molecules or particles or atoms? A chemist is never going to count out, 10 atoms or 10 molecules. That's impossible. All right? So we don't talk about individual atoms or molecules or particles. We have to talk about huge quantities of them because even in a small amount of water, a mouthful of water, you've got a tremendous number of water molecules. Unbelievable amount. So we can't talk about individual ones. We need a larger quantity. Just like somebody might have, instead of just one egg, you might have a dozen eggs. All right? That quantity that chemists use to talk about a group or a large quantity of particles, that is your mole. All right? And in chemistry, you never talk about, usually like when you do a lab experiment, you don't measure out and count the number of particles that you're going to use in a reaction. You mass them. You find out what the mass is. So we're going to have to, in this lesson, we're going to have to go between number of particles, moles, to mass. And from mass back to moles. Okay? So that is basically going to be the crux of what we're going to talk about is how can we talk about mass, number of particles, and we're going to use moles in order to go between number of particles and mass. Okay? Let's look at Model 1. Model 1 is helping you understand the concept of a mole by helping you understand something that you would be more familiar with, and that would be working with something that we count using a special number. That number would be like a dozen. Okay? So let's say we have a whole bunch of eggs, chicken eggs or quail eggs, and we have a number of eggs. We count them up. We then mass that whole sample for each chicken and quail group, and then we're going to look at ratios over here. So let's answer these questions. Consider the data in Model 1. What is the mass of a standard chicken egg? That would be like the average. Not every egg is going to be exactly the same, just like not every isotope of an element is going to have the same mass. It's going to be basically an average, or like a weighted average we talked about. So in this case, the mass of a standard chicken egg, if you've got one, it is basically on average 37.44 grams. Okay? What is the mass of a standard quail? Standard, if you just have one, is 2.34 grams. Mathematically, show how the 16:1 ratio of masses was calculated in the last column of Model 1. So ratio of masses of the eggs, 16:1, basically you're taking the 37.44 and dividing by the 2.34, and you're getting 16. So that means it's a 16:1. Okay, 16:1 ratio. We're going to then now use our calculator, and we're going to fill in this Model 1 here. I'm not going to do all the calculations. I'm just going to set them up. You can take your calculator and do the calculations with your calculator. Okay? Divide the work. Yep. If we have a group, if you have a bunch of people working with you, great. Always reduce all ratios to the lowest whole numbers if possible. So, number of eggs in the sample, if you know that 1 is 37.44, then if you've got 10, you're going to do 10 times 37.44. Here you're going to do 438 times 37.44 to get this number. Okay? A dozen, well, you take 12 times 37.44. And for a million, you're going to take a million times 37.44. You can do all of that. Same thing over here, you're going to do exactly the same thing, but now you're going to multiply by 2.34, which is the mass of an egg for your quail. I'll let you do that. The ratio of numbers of eggs. So here we're doing a 1-to-1 ratio, a 10-to-10, which is also 1-to-1, 438 to 438, also 1-to-1, a dozen to a dozen, a 1-to-1 ratio, a million to a million, 1-to-1 ratio. All of these are 1-to-1 ratios. And if we look at the masses, you're multiplying by the same number. So in all of these cases, you're going to have a 16-to-1 ratio for all the masses as well. Okay? Imagine you have two baskets, one filled with quail eggs and one filled with the same number of chicken eggs. Which basket would be heavier? So if you have, look back up here, it's really simple. If you had two baskets, one filled with quail eggs and one filled with the same number of chicken eggs, the chicken eggs, each individual chicken egg is heavier. So as a result, if you had one of each, obviously the basket with chicken eggs is going to be heavier because each individual one is heavier. Even though you have the same number, the unit mass is larger. Okay? How many times heavier would that basket be? Well, it's going to be 16 times heavier because the masses are in a ratio of 16-to-1. And how is it possible for you to answer part B with confidence even though you don't know the exact number of eggs? Because looking back up here, you always know the chicken and the quail eggs, the masses are always in a ratio of 16-to-1. Okay? Looking at the ratio of masses. A farmer weighs out 32 kilograms of chicken eggs. By the way, that is, for grams, 32 kilograms, there's 1,000 grams in a kilogram. So this is 32,000 grams. What mass of quail eggs would he need to weigh out to have the same number of eggs in both samples? So if you look here, it doesn't say how many chicken eggs you have. It just says the mass. And that's the same in chemistry. We don't count out how many particles when we do a reaction. We count out the mass of a particular compound or the mass of a particular element. But we often want to know how much of that do we have? How many do we have? So we have to know what is the mass per dozen particles. Like we're doing a dozen eggs here. But it's a mole. What's the mass per mole of particles in chemistry? What mass of quail eggs? So, if you have 32 kilograms of chicken eggs, if I was to find out how many chicken eggs that is, I could, or I could just use my ratio up here, 16-to-1. So, 32 kilograms of chicken eggs, that's probably a lot of chicken eggs because it's 32,000 grams. But I know that the chicken eggs and quail eggs are in a mass ratio of 16-to-1. So if I take 32 and I divide by 16, I'm going to get 2. That should be 2 kilograms. Or basically, the ratios are going to be always a 1 to 16 or 16-to-1. So you're basically saying 1 to 16 has to equal what to 32? You're setting up a proportion, and you're solving for this number right here, which has to be 2. If the farmer had weighed out 32 pounds of chicken eggs rather than kilograms, what mass of quail eggs would he need to weigh out to have the same number of eggs in both samples? Well, just because it's pounds or kilograms, the mass is still going to be a 16:1 ratio. It's not dependent on what unit you're using. You just have to make sure that the unit is the same for both eggs. So if he weighs out 32 pounds of chicken eggs, then the mass of quail eggs would need to weigh out to have the same number. It's going to be the same thing, 2 pounds. Okay? All right, it says here, a farmer makes up a new counting unit called a cluster. All right, whatever that is, but we're going to find out. If the farmer had 3 clusters of chicken eggs and 3 clusters of quail eggs, what could you say about the ratio of their masses? Well, 3 clusters of chicken eggs and 3 clusters of quail eggs, this is number. This is a counting unit. So if you have the same number of both, the masses, though, are always going to be in a 16:1 ratio. The chicken eggs are bigger. How much bigger? 16 times heavier. So what could you say about the ratio of the masses? Still 16:1. Okay? If we have, in part B here, does it matter in this problem how many eggs in the cluster? No, it doesn't matter. The number doesn't matter because we have this set ratio. Okay? All right, let's take what we learned in the egg model and apply it to atoms. Here we go, some chemistry. Like eggs, atoms of the same element may have slightly different masses. As I mentioned, isotopes. But on average, we use an average atomic mass. All right, we're going to use that average atomic mass for each element. These masses are recorded in atomic mass units, where 1 AMU is approximately equal to the mass of a proton or neutron. So AMU, atomic mass unit, is the unit used to measure the mass of tiny particles. Okay, so it's a very, very small unit. But we really don't use AMUs, we use grams. And you're going to see how this plays out in a second. Okay? So let's say we have oxygen and sulfur, just like we had chicken eggs and quail eggs. Number of atoms, mass, and you can see where this is going, right? And these numbers here have been rounded for us. So a single atom of oxygen is about 16 atomic mass units. A single atom of sulfur is about 32 atomic mass units. That's a tiny, tiny unit, by the way. All right? And we see here, number 6 says, what is the ratio of the mass of an oxygen atom to the mass of a sulfur atom? And if we go oxygen to sulfur, this is oxygen to sulfur. It is, let's fill in this table, by the way. You'd get it the same way, right? You'd multiply this by 16, you'd multiply this a dozen, 12 by 16, multiply this by 16. A mole, they already put that in there for you. A mole, by the way, is 6.022 times 10 to the 23rd. It's just a number. And they tell you it's 16, oh, interesting, grams. Hold on to that. Here we'd multiply by, oops, sorry, that's already done, times 32, 12 times 32, times 32, okay? Ratio of number of atoms is always going to be 1 to 1 all the way through here. And let's look at the ratio of the masses. 16 to 32. So 16 to 32 is a 1 to 2 ratio for all of these. All of them are 1 to 2. The sulfur is twice as heavy as the oxygen. So any quantity of sulfur is going to be twice as heavy as the same number of oxygen atoms. One to 2 ratio. Fill in the table in Model 2. We just did that. And circle the phrase below that completes the sentence. When 2 samples contain the same number of atoms, the masses are going to be the same? No. the ratio of the sample masses will be equal to the ratio of the atoms' masses. Yes. The ratio, doesn't matter how many you have, the ratio of the masses is always going to be the same, as long as you have the same number of both. Okay? Explain why it is not necessary to know how many atoms are in 1 mole to finish the last row of the table, because all you care about right here is the ratio. So if you've got 16 grams and you're told that that's 1 mole, and over here you got 32 grams and you're told that's 1 mole, hey, these two masses are in a 1-to-2 ratio, so you must have the same amount of both. It must be a 1-to-1 ratio there. Okay? I'm just going to point something out here. Look how neat this is. It's not by mistake, by the way, that this 16 AMU, different unit than a gram, but this 16 AMU is the mass in atomic mass units of 1 oxygen atom. Down here, this number, a mole, is specifically to give you the number of oxygen atoms that is going to give you a mass of 16, same number, but grams, different unit. We're going to work with grams way more often than we do AMUs. We're never going to use AMUs in the lab, okay? So the way this mole works is the exact number that gives us the mass in grams, such that the number here is exactly the same as the atomic number, but the unit is grams. So a mole of oxygen is going to have 16 grams. It's going to have a mass of 16 grams, and 1 oxygen atom is going to have a mass of 16 AMU. A mole of sulfur is 32 grams. 1 sulfur is 32 AMU. Okay? This number right here, 32 grams, is called the molar mass, the mass of 1 mole, molar mass for sulfur. 16 is the molar mass of oxygen. Okay? All right. Because here, again, we don't care how many, the ratio is always going to be the same. The ratio is constant. Okay? The ratio is constant. Key point here. How would the number of oxygen atoms in a 16-pound sample compare to the number of sulfur atoms in a 32-pound sample? Hey, as soon as I see that they are in a 16 to 32 or 1-to-2 ratio of the masses, I know that I have equal numbers of both. I don't know how many. Because this is pounds, not grams. I don't know how many. I just know that I've got the number of oxygens is going to equal the number of sulfur, because their masses are in this ratio of 1-to-2, according to the ratio of the molar masses. In the front of the room, there's a bottle that contains 32 gram sample of sulfur. This is 1 mole of sulfur. Estimate how many atoms are in the bottle. Your group must reach consensus. Okay, so a mole, I already kind of told you this, but a mole is a huge number. 6.022 times 10 to the 23rd. That is basically 6 with 23 zeros behind it. It's huge. And if I've got 32 grams and I look back up here, 32 grams is the molar mass of sulfur. The number of particles I have is 1 mole, 32 grams. And what is 1 mole? It's just a number. It's a very special number. It's a number here that gives me a mass of that element equal to the atomic number. So I know that I would have a mole, and there are 6.022 times 10 to the 23rd sulfur atoms in that bottle. So the relative masses of the element can be used to count atoms. If we know what the molar mass is, If you measure out a sample equal to an atom's atomic mass in grams, you always end up with the same number of atoms. That is your mole. A quantity of any sample whose mass is equal to its atomic mass in grams. We're going to use grams, okay? That's what a mole is for us. So, if you have one atom of hydrogen, if you look on the periodic table, one atom of hydrogen has an atomic mass unit of about 1, right there. 1 mole of hydrogen, 6.022 times 10 to the 23rd, has a mass of about 1 gram. 1 gram. 1 atom of copper, 63.55 AMU. But a mole of copper, 63.55 grams. Same number. How convenient. That's what a mole does for you. Okay? A molecule of oxygen, by the way, look, see it's O2 here, by the way. Remember, oxygen, the molar mass is 16, but it's O2, so twice as heavy if it's O2, 32 there. So a mole of oxygen molecules, O2, is 32 grams. Over here, all of these numbers, these are called the molar mass in grams. Molar mass. Molar mass. All of these numbers are the molar mass of those particular elements. Okay? Every element or compound has its very unique molar mass. In fact, it's often used to identify what you have if you can find the molar mass. Okay? The number in each element box used to find the values of the average mass of a single particle. So that is the atomic mass. Okay? Every element has its own atomic mass, atomic mass, atomic mass. Remember, it is the weighted average of all the masses of the isotopes. Atomic mass, atomic mass. All of these numbers are going to give you that number would be the number of AMUs for one atom, and this number is going to also give you the number of grams for a mole, 1 mole of that atom. Okay? Same number, different units. Same number, AMU for an atom, grams for a mole. How is the mass of a single particle changed to give the mass of 1 mole? And we change the AMU, we change it to grams. Okay? Which sample contains more atoms? 18.016 AMU of water or 18.16 grams of water? Well, more. Which one has more atoms? That's 1 particle. All right? This is the mass of just 1 molecule. This is the mass in grams, you got to watch those units, of a mole of particles. Huge quantity. So obviously the grams does because that is the mass of 1 mole. This is just the mass of 1 molecule. Key point. If the formula mass of iron 2 sulfate is FeSO4 and its formula mass is 151.9 AMU, that's for a single compound, what is the molar mass of iron 2 sulfate? It's going to be exactly the same number, but what will the units be? Grams. Easy. By the way, how would you get this 151.9 grams if you were not given the total molecular mass? Well, you would find on a periodic table iron, sulfur, oxygen, and add up their individual atomic masses. 1 iron, 1 sulfur, 4 oxygens, and you'd find those individual atomic masses on the periodic table. Iron, 55.845. You can probably round it off the nearest tenth. Okay, iron, sulfur, 32.1, oxygen, 15.99, so 16, four of those. So you take 55.8, 32.1 plus 4 times 16, whatever number that is. Well, we know what it is actually. It's 151.9 approximately. That's how you get the molar mass of any compound. Okay? It would be in grams. It would also be the molecular mass in AMU, or formula mass sometimes called. Use a periodic table to calculate the molar mass of ammonia. So here we go. 1 nitrogen, 4 hydrogens. Nitrogen, I just look on the periodic table. Nitrogen is going to be about 14, I believe. There it is, 14. Hydrogen is 1. So let's just round off for ease of computation. 14, 4 times 1, so it's going to be about 18 grams for ammonia. How would the number of atoms in a 1.01 gram sample of hydrogen compare to the number of atoms in a 63.55 gram sample of copper? Okay, look right here. Let's find these numbers and see how they relate to our different elements. Hydrogen, copper. 1.01 grams of hydrogen. That is the molar mass of hydrogen, because here's the atomic mass. So if it's in grams, that would be the mass of a mole of hydrogen. And if I look at copper, 63.5, oh, that's the molar mass of copper. So if I've got this mass in grams, I've got 1 mole of copper. And if I've got 1 gram of hydrogen, that gives me 1 mole of hydrogen. Because hydrogens are so tiny compared to copper. So a mole of each, of course, the mass of the hydrogen, the mole of hydrogen is going to be so much less than the mass of a mole of copper. Okay? But you would have a mole of each of them, because you look in the periodic table, those are the molar masses that were given to us. So here's your molar mass of hydrogen, here's your molar mass of copper. I must have a mole of both. So how many things are in a mole? By estimating the size of atoms and taking volume measurements of 1 mole samples, scientists can estimate that a mole is 6.022 times 10 to the 23rd. Look how huge that number is. Isn't that amazing? Okay? This number is called Avogadro's number because it's named after the scientist who discovered it. So let's fill in the blanks below using a periodic table. And make sure we are aware of grams or AMU. Let's just point out a few things here. Let's just make some observations. If we're talking about a single atom, AMU. If we're talking about moles, you better use grams. Okay? If we're talking about a specific formula unit, like just 1 molecule of that, AMU. If we're talking about a mole, grams. Okay? So 1 atom of helium has a mass of what? Let's look at our periodic table and let's go to helium. Look right there. That is the atomic mass of helium. So 1 atom of helium has a mass of about 4, get the right unit, AMU. Okay? 1 mole of helium contains 6.022 times 10 to the 23rd atoms and has a mass of what? Well, if you wanted to, you could take 4 times this number and get the number of AMUs, but we don't. When we're talking about moles and we're talking about this many particles, we're going to use grams and not AMUs. So it has a mass of 4 grams. Okay? 1 formula unit, a single compound of calcium chloride has a mass of what? I look at my periodic table and we have calcium, I think it was calcium chloride, right? Calcium chloride, CaCl2. So Ca 40.1. I'm just going to go 40, just ease of calculation here. You can use a calculator if you want. And Cl, so 35.5. So 35.5, and I've got CaCl2 here. So you've got 1 calcium and 2 chlorine. 35.5 times 2, that's going to give me 71. And my calcium was the 40.1 or 40 about. Okay, so when I add these two together, I'm going to get my my formula unit of calcium chloride has a mass of, add these two together, I'm going to get 110, about 110.1, okay? Or 111, sorry, 111.1, and this is AMU, because we're talking about a single unit. Now a mole of this contains 6.022 times 10 to the 23rd units. That's how many different units I have. And it has a mass of, I'm not going to record this in AMUs anymore. I'm going to say the same number, but in grams. Easy. Easy, easy, easy. Okay? All right. In our extension question here, we have, it says, use a periodic table to answer the following questions. Fluorine gas consists of diatomic molecules of fluorine. F2, always F2 in nature. How many molecules of fluorine are in 1 mole of fluorine? So molecules. This is 1 molecule. So F bonded with another F. That counts as 1 molecule. Don't count it as 2 just because it has F2. That's 1 molecule. So in 1 mole of fluorine, there are 6.022 times 10 to the 23rd molecules. A mole of anything is that number right there. Okay? And what is the mass of 1 mole of fluorine gas? So the mass of 1 mole of fluorine gas, so F2, we have to be careful here because if we look on our periodic table, F has a molar mass of 19, 18.998, okay, 19. But I'm not just working with F, I'm working with F2. So the molar mass of F2 is 2 times 19. So it's going to be 38 grams per mole. Okay? What is the mass of 1 mole? So the mass of 1 mole is going to be 38, not just 19, because you've got 2 in there per unit. Okay? How many atoms of fluorine are in this sample? Atoms now, not molecules. Atoms. Well, in each unit you've got 2, and if you've got a mole, 2 times a mole of molecules, you're going to have 2 moles of atoms, which is 2 times Avogadro's number, so that's going to be 12. You know, you're going to take this and multiply by 6. 12.044 times 10 to the 23rd. Okay, just multiply that by Avogadro's number. Okay, last one, number 20. We have the mass of 1 mole of lead is 207.2. That must be its molar mass. We are told that that is the mass of 1 mole. Use a proportion to calculate the number of lead atoms, still lead, in a 15-gram sample of lead. So, all you're going to do is, you're going to say, if 1 mole has a mass of 207.2, then how many moles is going to have a mass of 15? And you're just going to cross multiply and divide. So we're going to have basically 15 divided by 209.2 is going to give you your number of moles. And that's going to be a decimal value. It's going to be a fractional number of moles. And then if you want to find out how many actual particles that is, you're going to take this value here and multiply by Avogadro's number, if you want to actually find out how many atoms. Okay? So, what is the mathematical relationship between atomic mass units and grams? Well, 1 gram is how many AMUs? Let's look at what we've been doing here. If you have 1 AMU for, let's say, hydrogen. Hydrogen has an atomic mass unit of 1 AMU about, and then you have 1 gram, then you would multiply by 6.022 times 10 to the 23rd in order to get the number of grams, right? That would give you the number of grams. Sorry, the number of AMUs. The number of AMUs in a mole of that. Okay, and that would give you, for hydrogen, that is 1 gram. So a gram is 6.022 times 10 to the 23rd AMUs. All right. All right. I hope this is helpful. I'm going to show you one last thing before we say goodbye, because I mentioned earlier that what you're going to have to do is be able to convert from moles to mass. Actually, it's mass to moles and then to particles. So I'm going to show you this really quickly here at the bottom of the page. You are often given the mass of something, and maybe you want to find the number of particles. So here's how you do that. You are always going to go through number of moles. If you're given the mass, and if you want to then find out how many moles that is, to go from mass to moles, you are going to have to use the molar mass. And how do you get molar mass? Straight from the periodic table. Straight off the periodic table. So if you know that you've got 2 grams of hydrogen, then you would divide by the molar mass of hydrogen to find out how many moles that is. If you've got 4 grams of hydrogen, if you've got 10 grams of hydrogen, divide by the mass for each mole to find out how many moles you have. So you would divide, that's a division symbol, by the molar mass. If you're given mass, divide by that molar mass to get the number of moles. If you then have the number of moles and you want to go to the number of particles, you want to find out how many particles that is, you multiply by Avogadro's number, 6.022 times 10 to the 23rd. Okay? Let's go the other direction. Let's say you know the number of particles and you want to find out how many moles that is. That's where you divide by Avogadro's number, 6.022 times 10 to the 23rd. And if you know the number of moles and you want to find out what's the mass of all those particles, you would multiply by the molar mass. Okay? So I hope that's helpful. This is kind of a little cheat sheet here, so that anytime you have to go from one to the other, you can use these operations to do that. Notice you're always going through moles in order to go from particles to mass. At least that's one way to do it. Okay? If you don't know the conversion here to go straight from particles all the way over to mass. Just go through moles using Avogadro's number and the molar mass. Avogadro's number is a fixed number, never changes, 6.022 times 23rd, times 10 to the 23rd. And the molar mass, where do you find the molar mass? Right on the periodic table. It's this number right here in grams. Every element has its own unique molar mass, and it is the atomic mass, but in grams. Okay? All right. I will see you in the next video.